Hey 216ers, I'm CJ Nygaard, one of your TAs for Professor Kaufman's 216 classes, and today, February 26th, I'm going to be going over what we talked about in discussion. So today we talked about bitwise operations, and since most people hadn't heard much about them before, we kind of started from the beginning and worked down with some examples. So I'm going to go over some examples and teach you all about them, and then we'll go over into some code and see what they look like in C. All right, so bitwise operations is what we talk about today. So what are bitwise operations? They're basically taking the bits of numbers and performing different operations on the individual bits rather than on the entire number. So we have a bunch of bitwise operations, about 6 different operators that we can use. So we have an ampersand, and the ampersand is the bitwise AND operator. We have a pipe, which is a bitwise OR. We have a caret, or a little up arrow, which is a bitwise XOR. We have a tilde, which is a bitwise NOT. We have a 2 left arrows, which is left shift, and we have 2 right arrows, which is right shift. All right, so these are our bitwise operations, and we'll just go down a list of them and I'll show some examples. So first, for the ampersand bitwise AND. So let's say we have a number 0, 0, 0, 0, 0, 1, 1, 1. That is the number 7. If we then have the number 12, which is 0, 0, 0, 0, 1, 1, 0, 0. If we AND these two together, we basically, on every single bit, so on these bits, do an AND, on these bits, do an and so on, all the way until the end. So first, we'll go left to right here. We go, I guess I'll denote these. This is bit 0, bit 1, bit 2, bit 3, 4, 5, 6, 7. So starting from 0 and going up, just like indexing, I'll just start from index 7. You can go either way. I'll just go left to right. So 0 and 0, we get 0. 0 and 0, 0, 0, 0. 0 and 1, we get 1. 1 and 1, we get, 0 and 1, we get 0. 1 and 1, we get 1. Then we get 0 and 0 for the other two. So this is a bitwise and we end up with the number 4. So that is a bitwise and. You take 2 numbers, one on the left and one on the right, and an and in the middle. So like A and B, or I suppose 7 and 12 equals 4. All right. So that is bitwise and. Now let's go down. We have bitwise OR. So OR is the same thing. Not the same thing. OR is very similar though. I will use the same examples. 0, 1, 1, 1 equals 7, 0, 0, 0, 0. And by the way, these are all characters, but we're calling them numbers. That is 12. And if we want to OR them together, well, 0 or 0, 0, 0, 0, 0. 0 or 1 is 1. 1 or 1 is 1. 1, 1. So then we end up with, let's see, what is that? 15. So 7 or 12 equals 15. All right. Now I'll go to a new page, bitwise XOR. So exclusive OR means one or the other, but not both. So again, with our 7 and 12, 0, 0, 0, 0, 1, 1, 0, 0 equals 12. With 7 and 12, we have 0 or 0, 0. 0 or 1 is 1, but 1 or 1, well, it's an XOR, so 1 XOR 1 is 0. And then these last two are 1s. So now we have the number, well, let's see. We have 8, so 11. Is that 11? Yes, that's 11. Okay, so 7 XOR 12 equals 11. Great. Now on to the NOT operator. The NOT operator is like the NOT operator in C, the exclamation mark, where in the sense that it only takes one number, so we will use 7 again. So 0, 0, 0, 1, 1, 1 equals 7. Well, not that is going to be, we flip every single bit. So if it was a 0, now it becomes a 1. And if it was a 1, now it becomes a 0. And so this, I'm not going to do the math on what that number is, but we flip every single bit. And we'll talk about that one later. Okay, so now we have left shift and right shift, which are very similar. Left shift, again, with our example, equals 7. If we do 7 left shift by 3, then we will move every single bit over 1, 2, 3 spots. And so left shift, and so for every single bit in this, we move it over 3 spots. And all of these bits, so for example, these 3 in the bit shift 7 over by 3, these are all thrown out into the void, and we don't care about them anymore. So here we have 0, 0, 1, 1, 1, and then we just add 0, 0, 0 for the rest of those. And so, color, make it red. All right, so we just shifted all 3 of those 1s there over 3 to the left. All right, and we just added zeros where in the new place. Okay. Shifting right now, again, 0, 0, 0, 0, 1, 1, 1 equals 7. It is the exact opposite. So let's do 7-bit shift. Let's just do 1 over. Well, we're going to put a 0 here. Then we're going to have this one goes there, 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 there. All of these go over. So 0, 0, 0, 0, 0, 1, 1. And this last one, since we've already filled all of our bits, that last one gets thrown out into the void. And, well, so let's see, what does this number up here equal in the bit shift left? Well, we bit shifted 3 over, and since we're working in base 2, I can say that we multiplied by 2 3 times. So first 7 times 2 is 14. 14 times 2 is 28. And then 28 times 2 is 56. And so I believe if you do the math on what the binary number there is, it should be 56. And I can check that for myself right now. Yes, indeed that is 56. All right. So we are multiplying by 2 each time. And so, and then for the right shift, we are dividing by 2. And so this is 3 because the last little bit gets cut off. The remainder of the division gets cut off. And so that's an interesting little factoid, is that let's say you have the number 12. If we do like a decimal shift, a binary shift, but a decimal shift over 1, we get 120, which is 12 times 10, because we're working in base 10. But then in binary, we multiply by 2, because we're working in base 2. All right. So with all of those rules, let me check that I haven't missed any. Okay. With all of those rules, we can do some pretty interesting stuff. Let's say we have a number 0, 1, 1, 0, 0, 0, 1, 0. And we want to check if bit number, well, so we have 0, 1, 2, 3, 4, 5, 6, 7. Let's check if bit number 5 is set. Well, let's do a bitwise AND with the number 0, 0, 1, 0, 0, 0, 0, 0. So this we call a mask because we are only checking bit index 5. So bit 5, we are only checking that one, and so we mask. Everything else is 0 except for bit 5. And then we AND it together, and so we see here 0, and so 1 and 0 is 0, 1 and 1 is 1, and then all of the rest of these are 0. If that does not equal 0, then we know that that bit is set. I'll do an example. If that bit was not set, then we would get a 0 here, and the entire thing equals 0. Okay, so that's checking if a bit is not set. Oop, what did I do? Okay, let's now set this bit. How would we set this bit? Well, how would we set this bit? We could do a bitwise OR. So I'll put this in red. I'll put it in blue so that we can see that it's a bitwise OR and not a 1. And then we do the same thing. We do 0, 0, 1 because we're setting that bit, 0, 0, 0, 0, 0. And what do we end up with this OR? Well, we get 0, 1, 1, 0, 0, 0, 1, 0. And so as we see in this first number, we have the same number down here, except this 5th bit is set. All right. So now, what if we want to unset a bit? So let's say this bit was 1, and we want it to be 0. Well, here we would AND with 1, 1, 0, 1, 1, 1, 1, 1. So everything is 1s except for that bit that we want to unset. And so if we see here, 0, so from the 7th bit, 0 and 1 is 0. 1 and 1 is 1. 1 and 0, well, now we set that to 0. 0 and 1 is 0, 0, 0, 1, and 0. And so we have this number. Now we have unset this 5th bit in the result. All right. Now, what if we don't care what the bit is? And additionally, if the bit was already unset, it was already 0, then this just remains 0. Okay, what if we don't care what that 5th bit is and we just want to flip it? We want to toggle it so that that single bit, nothing else in the number, is the other one. So if it was a 0, now we wanted a 1, and if it was a 1, now we wanted a 0. Well, we would do a bitwise OR, and we would do 0, 0, 1. Oops. Sorry, a bitwise XOR, 0, 0, 1, 0, 0, 0, 0, 0. Oh, yes. Okay, so again, 0 XOR 0 is 0. 1 XOR 0 is 1. 0 XOR 1 is 1. 0, 0, I'll fill in the rest. And we see that we have now, that is now a 1, but it was a 0. Okay, let's look at the example though that was exactly opposite. So it was a 1. Well, 1 XOR 1 is a 0. And so once again, we have flipped it. All right. So let's go back to that AND example. And we have 1s everywhere except for this bit. So once again, that is unsetting that bit. Well, how do we create this number? Do we write it out each time? No. All right, sorry about that. Had some technical difficulties. Okay, back where we were. How do we create this number? This, do we write out every single bit every single time? Well, that can be a bit tedious if we're using things like integers instead of characters. We would have to write out 32 bits. No, maybe. Yeah, we'd have to write out 32 bits every single time and get it right. And what if we want to test different bits at different times? Well, then we'd have to write out every single possible check. And so instead we can use bitwise operations to create this number right here. So let's look at that. Well, let's just start with the number 1. And if we are trying to get over to position 5, well, 1 starts here, and we go 1, 2, 3, 4, 5. And so we actually want to bit shift 1 over 5 spots. So that would create 0, 0, 1, 0, 0, 0, 0, 0. And now we have this number is completely opposite from this number. And how do we solve that problem? Well, if it's completely opposite, every single bit is different, then we just use the bitwise not. And so that will then flip every single bit, and we end up with 1, 1, 0, 1, 1, 1, 1, 1. Perfect. And so now we can easily just AND that number. Well, I suppose put it in parentheses. We can easily just AND that number with our target number. And so whatever this target number is, well, let's just call it X. So we set X equal to X and this number, and we will flip that bit. All right. So we have discussed, well, we've discussed our bitwise AND, our bitwise OR, our bitwise XOR, our bitwise NOT, our bitwise left shift, and our bitwise right shift, and how to use them. We've discussed checking if bits are set. I'll leave it to the viewer to figure out how to check if bits are not set. We've figured out how to set bits ourselves, how to unset bits, and how to toggle bits regardless of the state of that bit. Now let's jump over into some code examples. right, so that's pretty much it, other than in the very first part of this video, I forgot to mention that you can do that same bit mask where you have everything is 0 except for one bit, except you can do multiple bits in the bit mask, and you would then be testing multiple bits at once. So you don't have to test one bit at a time. All right, but other than that, that is today, February 26th discussion. You might relearn a lot of this tomorrow in class. I'm not too sure, but hopefully this sets you up perfectly for moving forward into this week's Lab 5 and Project 2, which should come, I don't know, tonight or tomorrow, somewhere around that. All right, good luck with all of those. Have a good day, and I'll see you all, I suppose, Wednesday, some of you.